Welcome to this custom-tailored deep dive. We've got a really great one for you today.
Yeah, we have a massive stack of sources to get through.
We really do. It's a dense stack of technical networking chapters. We're talking device management protocols, NAT, quality of service, first hop redundancy.
It's basically the instruction manual for how the modern world actually communicates.
Exactly. Our mission today is to decode the invisible plumbing of the internet, the stuff you use every single day, but completely take for granted.
Right, because when it works, it's entirely transparent.
But the reality is, the infrastructure you rely on is held together by these absolute miracles of engineering. I mean, operating completely behind the scenes.
And we are going to synthesize all these sources to figure out exactly how those miracles happen.
So to set the stakes for you, we're really looking at a couple of major technical hurdles. First, why didn't the internet just completely run out of IP addresses back in the 90s?
Because it absolutely should have. The mathematical limits were right there.
Yeah, everyone predicted a total collapse.
Yeah.
And second, why doesn't your enterprise VoIP phone call sound like a skipping CD when everyone else in your office is downloading massive file updates at the exact same time?
It's a constant battle of traffic engineering.
Now, we're going to unpack all of that. But to understand how all this traffic flows, I think we really need to start with the management side of things, right?
Yeah, you have to. Network administrators have to know what their hardware is actually doing.
Which brings us to system message logging, or Syslog.
Right. Cisco devices, for example, they're constantly generating these log messages, internal states, temperature changes, protocol drops.
But the sources emphasize this isn't just some random text dump. There is a very strict hierarchy here.
The severity levels.
Exactly, running from level 0 all the way down to level 7. Level 0 is a full-blown emergency. Like, the system is unusable, catastrophe.
Right, the building is on fire, hardware is melting.
Yeah, and then it steps down. Critical error, warning, all the way to level 7, which is just called debug.
And that is where an engineer can get into serious trouble.
The debug command.
Yes, because if you turn on a broad debug, say you tell the router, monitor every single routing packet that crosses this interface and write a log for it.
That sounds useful, though.
It is, but it forces the router's main CPU to process those messages. It takes processing power away from actually forwarding the network traffic.
Oh, wow.
It's like trying to drink from a fire hose. The CPU gets so overwhelmed just writing the level 7 logs that it stops maintaining its routing tables.
So you could literally crash a production router just by asking it to log too much information.
You can completely lock it up. It's a classic self-inflicted denial of service.
That's wild. Which I guess is why the sources say you should send logs to a centralized Syslog server instead of printing them out locally.
Exactly. Offload that processing burden.
Okay, but speaking of those logs, they're kind of useless if the timestamps are hallucinated.
No, absolutely useless.
I mean, imagine you're troubleshooting a dropped connection across a massive corporate network. Router A drops the connection and logs it at 1:40 p.m.
Right.
But router B, whose internal clock has been slowly drifting for the last 6 months, logs that exact same drop at 9:45 a.m.
Good luck correlating those events. It becomes a total nightmare trying to find the root cause.
Which is why we have NTP Network Time Protocol.
Right. It's not just about knowing what time it is. It's about absolute topology-wide synchronization.
And the mechanism it uses for this is fascinating. The stratum levels.
Stratums, yes. It's a hierarchy of truth.
So stratum 1 is the absolute top tier. That's usually an atomic clock or a highly precise GPS clock like the ones run by NIST.
Right, the government time servers.
Yeah. So if a router asks that NIST server for the time, that router becomes a stratum 2 device.
It's one hop away from the ultimate source.
And if an access switch pulls its time from that stratum 2 router, the switch becomes stratum 3. It just cascades down the tree.
And devices are programmed to always trust the lowest stratum number they hear.
But there's a safety mechanism built in, right? The poison pill.
Yeah, the stratum 16 limit. If a device calculates that its time source is 16 hops away, stratum 16, it just flags the time as totally invalid.
Just throws it out.
Exactly. It prevents some wildly inaccurate broken clock from accidentally infecting the whole network architecture.
That's incredibly smart. The sources also mention a really cool trick for keeping NTP available. You don't bind it to a physical cable port.
Right, you use a loopback interface.
Because if you tie your clock synchronization to a physical port and a technician accidentally yanks that cable.
You lose your time sync instantly.
Yeah. But a loopback is virtual.
It's a logical interface. As long as the router's operating system is running and there is any physical path to reach the router, that loopback stays up.
It totally divorces the protocol from the physical hardware failing.
Which is a huge theme in network engineering, assuming the physical layer will eventually fail.
And that assumption extends right into how these devices even find each other in the first place. You plug a new switch into a rack, it needs to know who its neighbors are.
Right, layer 2 adjacency.
Yeah, and that is handled by CDP, the Cisco Discovery Protocol, or the open standard one, LLDP.
They're constantly sending out these multicast frames. The second you connect two devices, they start blindly sharing their telemetry.
Host names, what hardware model they are, the exact operating system version.
It's incredibly efficient if you're trying to map out a topology.
But the sources throw a massive red flag on this from a security standpoint.
It is a huge vulnerability if you don't manage it.
Because think about it from an attacker's perspective. If CDP is just running by default on a public wall, jack-like in a hospital waiting room or a corporate lobby.
Anyone can walk up and plug in.
Right. You plug in a laptop with a packet capture tool and without even needing an IP address or a password.
The switch just freely hands you a message saying, "Hi, I'm a Cisco Catalyst 9300 running iOS version 16.9.
You just gave the hacker the exact blueprint they need to look up known exploits for that specific software.
It's recon made easy. That's why the fundamental rule is you have to disable these discovery protocols on any port that faces the public.
Discovery is only for the internal trusted network.
Exactly.
Okay, so that's the local management side. Let's zoom out to how these internal networks interact with the wider internet, the great IPv4 crisis of the 90s.
The math was terrifying back then.
It was. The IPv4 architecture is 32-bit. That gives us a hard limit of roughly 4.3 billion addresses for the entire planet.
Which seemed like plenty in the 70s.
Right, but by the mid-90s, the internet was exploding. We were going to run out. It wasn't a theory, it was a mathematical certainty.
The entire global network was going to grind to a halt.
So what was the solution? The sources outlined this multi-layered defense.
Right, first they brought in CIDR to stop wasting huge blocks of addresses, and then, crucially, RFC 1918.
Private addressing.
Yes, the subnets we all recognize today.
The 10-dot networks, the 192.168 addresses you see on your home Wi-Fi.
Those addresses are specifically designated as non-routable on the public internet.
So a huge corporation can use a 10-dot network to give IP addresses to 50,000 laptops internally.
But the second one of those laptops tries to pull up a website, that private IP cannot cross the edge router onto the internet. It would be dropped immediately.
Which is why we need network address translation, NAT.
Exactly. The router has to translate that private inside local address into a public inside global address.
But early NAT-like static NAT was just a strict one-to-one mapping.
Yeah, one private IP to one public IP.
And dynamic NAT just used a pool of public IPs. Neither of those actually solved the shortage. If you have 1,000 employees, you still needed 1,000 public IPs.
It conserved absolutely nothing. The real hero, the mechanic that actually saved the internet and kept IPv4 alive for decades, was PET port address translation.
Or what Cisco calls NAT overload. This is where it gets so incredibly clever.
It shifts everything up to layer 4 of the OSI model.
Right. So when your laptop starts a session, it generates a source IP, but also a source TCP or UDP port.
And PAT takes that private IP and translates it to the single public IP on the router's outside interface.
But here's the magic. It also translates the source port to a unique ephemeral port from its own pool.
Because that port field in the header is 16 bits long.
Meaning a single public IP address can theoretically multiplex over 65,000 concurrent sessions at the exact same time.
It's staggering. The router builds this massive stateful translation table in its memory.
So when Google sends the website data back, the router looks at the destination port, checks its table, and knows exactly which internal private laptop to forward it to.
It's a massive processing burden on the router. It's rewriting headers on the fly for thousands of packets a second.
But it worked. It successfully hid entire global corporations behind just one or two public IP addresses.
It was a masterpiece of engineering. But, just getting a packet translated and routed to its destination isn't always enough anymore.
No, especially not today. For real-time applications, the delivery has to be completely flawless.
Which brings us to QoS, quality of service.
Because all network traffic is not created equal. The sources list 4 main metrics that QoS is fighting against: bandwidth, delay, jitter, and packet loss.
Right, and different traffic reacts differently. If you're doing a massive file transfer and the network drops a packet,
PCP just handles it. It acknowledges the drop, slows down its window, and asks for the packet again. You might see your progress bar stutter for a millisecond.
But real-time UDP traffic, like a voice-over IP phone call, it doesn't have time to ask for retransmission.
It's live audio. You can't rewind it. The sources are very strict on the numbers here. For voice to work, one-way delay has to be under 150 milliseconds.
Jitter, which is the variance in that delay, has to be under 30 milliseconds.
And packet loss has to stay under 1%. If you violate any of those, the audio codec just falls apart.
You get robotic voices, drop syllables. It's awful.
So how does the network stop that massive file transfer from running over the fragile voice call?
Classification and marking. We have to identify the important packets and literally stamp them as VIPs.
Right, at layer 3, they use the DSCP field in the IP header. It's just 6 bits.
And the gold standard mark for voice is expedited forwarding, or EF.
Which is decimal 46. When a router sees a packet stamped with a 46, it knows this is strict priority voice traffic.
But that creates an immediate problem.
Yeah, an exploit vector. What stops you or me from going into our PC settings and tagging our, massive 4K video streams with that EF46 tag?
Making our Netflix traffic VIP.
Exactly.
Network engineers block that using trust boundaries.
The network edge inherently distrusts end-user devices.
Right. The switch port where your PC plugs in is configured to just strip away any QoS markings you try to apply. It rewrites them to 0. Best effort.
You only trust managed devices like a corporate IP phone.
Yes. The switch trusts the phone's markings, but ruthlessly polices the PC plugged into the back of that phone.
Okay, so the traffic gets legally marked. Then it hits the interface to leave the router. Now we have to talk about queuing. Who goes next?
Historically, routers used round robin.
Take a packet from QA, then QB, then QC. Very fair.
Fair, but terrible for voice. If a voice packet has to sit in a buffer waiting for an FTP transfer to finish its turn, your 30-millisecond jitter budget is destroyed immediately.
So they invented low-latency queuing, LLQ.
It creates a strict priority line. If an EF-marked voice packet enters the router, LLQ stops the round robin completely and sends the voice packet right now.
It literally cuts the line every single time.
Which is great for voice, but it creates queue starvation.
Right. If there's a huge surge of voice traffic and it always gets to cut the line, the regular data queues will never get a turn. The router will just sit there dropping standard traffic all day.
That's why you have to use a policer with LLQ.
You put a hard ceiling on the VIP traffic.
Say 30% of the link bandwidth. Voice gets strict priority, but only up to that 30% mark.
And if it tries to use 31%?
The policer steps in like a bouncer and just aggressively drops the excess voice packets.
It's ruthless. Which highlights the difference between policing and shaping. A policer drops or punishes traffic that goes over the speed limit.
But a shaper acts like a dam. It queues the excess packets in a buffer and delays them, smoothing out the flow.
But the sources point out this crazy quirk when you try to shape voice traffic. It has to do with the shaping time interval, the T-massa.
Yeah, this is a really fascinating detail.
If an engineer sets a shaper to a 1-second interval, the router might send its entire allowable quota of data in the first 200 milliseconds of that second.
Leaving the shaper basically asleep for the next 800 milliseconds.
Right. And if a priority voice packet arrives during that 800 millisecond nap,
it gets trapped in the buffer until the next second starts.
Which totally shatters the 150 millisecond delay limit. The call quality is ruined by the very tool trying to protect it.
So the fix is you have to drastically shrink that TMA interval.
To 10 milliseconds.
Exactly. You force the router to calculate and send tiny microbursts of data 100 times every second.
Guaranteeing that no voice packet ever waits longer than 10 milliseconds in that queue. It's such a precise, granular tweak.
But even with all that perfect queuing, buffers can still overflow during massive congestion.
And when a queue is 100% full, the router has to do what's called tail drop. It just discards every new packet that arrives, period.
Tail drop is catastrophic for TCP.
Because of the synchronization issue.
Right. If multiple TCP sessions all experience a drop at the exact same moment, all their congestion control algorithms react synchronously.
They all hit the brakes at the same time.
The whole network's utilization plummets, then they all slowly speed back up, hit the full queue again, and drop again.
It creates these massive oscillating waves of congestion, TCP global synchronization. So how do we stop it?
By using psychological warfare against the TCP protocol.
I love this part. The routers use congestion avoidance.
Long before the buffer actually fills up, the router intentionally starts dropping a tiny random percentage of packets.
Early drops.
Exactly. Because TCP is a polite protocol. When a sender notices that random dropped packet, It assumes the network is getting congested.
So it voluntarily slows itself down.
Yes. The router tricks the sending computers into slowing down at different times asynchronously.
Which prevents the queue from ever actually hitting 100%, neutralizing the threat of tail drop entirely.
It's brilliant manipulation.
Okay, let's bring this all home with the final layer of our deep dive. First hop redundancy protocols, or FHRP.
The ultimate safety net.
Because you can have the most immaculately designed network in the world. Perfect time sync, NAT overloading, 10-millisecond shapers, random early packet drops.
But none of it matters if the physical router connecting your office to the internet dies.
Right. In a normal setup, your computer is told, hey, your default gateway is this exact router's IP address. If the power supply on that router catches fire, your whole subnet is stranded.
Even if you have a backup router plugged into the same switch, your computer doesn't know its IP address.
So protocols like Cisco's Hot Standby Router Protocol, HSRP, fix this by creating a phantom router.
A virtual router. The primary and secondary physical routers team up and generate a virtual IP address and a virtual MSOT address.
So your computer is told that this virtual IP is your gateway. You have no idea what the actual physical hardware is.
Behind the scenes, those two routers are constantly whispering to each other with multicast keep-alives.
One is the active router, doing all the actual work.
And the other is the standby, just waiting and listening.
And the second that active router dies, the keep-alives stop. The standby router realizes it and instantly promotes itself.
It takes ownership of that virtual IP. It sends out a message to the switches saying, hey, update your MAC tables, traffic comes to me now.
And the craziest part is, if you're on a VoIP call, when that hardware fails, you might hear a sub-second blip in the audio, but the call doesn't drop.
Your computer never even knows a massive physical failure just happened. It's the pinnacle of resilient design.
It really is. So just to recap this incredible journey for you, when you open an app on an enterprise network, your hardware is silently mapped out by CDP.
Your timestamps are perfectly locked in globally via NTP.
Your private IP address is multiplexed with thousands of others into a single public IP using the stateful tables of PAT.
Your real-time traffic is tagged as expedited forwarding, jumping to the front of the line with LLQ.
Micromanaged by 10-millisecond shapers, shielded from global synchronization by random early drops, and the whole thing is protected from hardware failure by the virtual routing of HSRP.
The layers of abstraction are just phenomenal.
It's a lot to take in.
It is, but to close out this deep dive, I actually want to leave you with a conceptual shift that builds on our NAT discussion.
Oh, bring it on. Let's hear it.
We established earlier that NAT, specifically PAT, was engineered strictly as a mathematical patch for IPv4 exhaustion, right?
Yeah, to hide thousands of internal computers behind one public IP.
But an accidental downstream consequence of that architecture is that it fundamentally altered network security.
Wow.
Because an internal laptop doesn't have a routable public IP address, a hacker on the internet cannot easily initiate a direct inbound connection to it.
Because the NAT router's state table will just drop the traffic if there's no corresponding internal request.
Exactly. The NAT router acts as an implicit stateful firewall. We've spent nearly 30 years relying on this accidental security barrier.
It wasn't designed for security, but it provides it.
Right. But now the industry is migrating to IPv6, and the IPv6 address space is basically infinite. There are enough addresses for every single atom on Earth.
So the math problem is solved permanently.
Which means the core necessity for NAT completely ceases to exist. It becomes totally obsolete.
Oh, wow.
In a pure IPv6 architecture, every single device, your laptop, your phone, your smart thermostat, is assigned a global unicast address. They are all publicly routable from anywhere on the internet.
That is a staggering paradigm shift.
So the question to mull over as you digest all these sources today is this. When we finally strip away NAT and we lose that implicit layer of address hiding we've leaned on since the 90s, how does the fundamental philosophy of cybersecurity have to evolve? What happens when every piece of hardware you own is directly exposed to the global routing table?
That is an incredibly complex engineering challenge for you to consider, and honestly a perfect place to wrap up. Thank you for joining us on this custom deep dive into the hidden mechanics of our networks. The next time you experience flawless connectivity under heavy load, you'll know exactly the invisible acrobatics making it possible. Until next time.